About 15 seconds, everybody.
This is Talk of the Nation Science Friday. I'm Ira Plato. The last decade or so has been called the golden age of cosmology, as scientists gather new information about the size, the shape, the makeup of our universe. And some of the research provides an update, like the age of the universe, now set at about 14 billion years old. But some of the research results are very surprising, like the discovery that the universe is accelerating outward, propelled by some strange dark energy that makes up 2/3 of the universe. Or the continuing search for dark matter, which we can't see, but we can feel. And trying to explain these almost science fiction-like properties, researchers have had to turn their eyes from the very big to the very little, to the tiny world of subatomic particles, string theory, and beyond. This week, cosmologists are meeting in Cleveland to ask, how long can the golden age of cosmology continue? What do we know now, and what do we need to know? And where do we go from here? This hour we'll be talking with scientists at the meeting and getting their thoughts on where cosmology is headed. Of course, we'll be taking your questions. If you're in the audience at Stroh-Sagar Hall at the Case Western Reserve University, I invite you to step up to the microphone and ask a question. And if you're listening to the radio or on the web, give us a call. Our number is 1-800-989-8255, 1-800-989-TALK. More information, you're always welcome and invited to surf over to our website at sciencefriday.com. Let me introduce my guest. Dr. Lawrence Krauss is the Ambrose Swayze Professor of Physics, the chairman of the Physics Department at Case Western Reserve University. He's also the director of the Center for Education and Research in Cosmology and Astrophysics and the organizer of the conference. Stephen Weinberg is a Nobel laureate in physics. Dr. Weinberg also holds the Jack S. Josie Welch Foundation Chair in Science at the University of Texas at Austin. Dr. Netta McCall is a professor of astrophysics in the Department of Astrophysical Sciences at Princeton University. Dr. Michael Turner is the Rohner Distinguished Service Professor in the Departments of Astronomy and Astrophysics and Physics at the Enrico Fermi Institute. He's also the chairman of the Department of Astronomy and Astrophysics at the University of Chicago. Welcome back to Science Friday, all of you. Let me turn and talk to you, Dr. Krauss. Tell us why you're having this meeting. It seems like you would have plenty of stuff to research. Why you seem to be wondering where to go from here.
Well, Ira, you did a good argument for why we should have the meeting. We're at this crossroads. We've just had a decade of incredible. Can you hear me, Ira?
Yes,
okay,
just fine.
Okay, we just had a decade of incredible revolution in the field, but the results of it are a model that's completely inexplicable to us at the present time.
We don't know what most of the energy in the universe is. We don't know what most of the matter in the universe is. At the same time, we've had these great observations, and there are a whole bunch of new devices that are about to come online, and so it seemed a good time to sit back and say, where are we going and what's possible? At the same time, we have to do that with a little bit of caution. I began the meeting by presenting how we would have run this meeting 25 years ago, and the questions we would have asked then, in fact, many of them turned out to be related to things we now know are not true. So I think it's a difficult task we've assigned the scientists who are here, but I think it's a good time to look and say, well, what's possible?
What are some of them? I'm intrigued. What are some of those things we were talking about 20 years, 25 years ago that it turned out not to be true?
Well, at that time, we weren't sure of the existence of dark matter at all. We thought the universe was probably open and not flat, as we now know it to be. We had no inkling of the existence of dark energy. Those are the three major components of the universe, and we really, at that time, didn't know about them. At that time, particle physicists hadn't yet come up with the plausible candidates to be dark matter. Now there are a number of them, and we're looking for them not just underground on Earth here, but also in the next particle accelerator that's going to be built, the Large Hadron Collider. We may discover them. So the basic components of the astronomy and the cosmology and the particle physics, most of those weren't in place in 1978. And in fact, also the idea of extra dimensions, which is now occupying a lot of people's minds.
Extra dimensions, we'll have to get into that because that's the hardest thing, I think, for people to understand. I think they can get dark energy, dark matter, with all these Star Trek and stuff about extra dimensions, but getting your arm arms around it is a little, well, it's kind of small, so it's hard.
We already, this morning, it was clear, already it began to be clear that it's difficult for scientists to get their arms around it as well. So.
Well, that's good to hear. Dr. Weinberg, you agree that dark matter, dark energy, any other big issues?
I think those are the biggies. It certainly is a golden age for cosmology. It gives me a certain amount of pain to say that because I'm an elementary particle physicist and we haven't had this kind of excitement in elementary particle physics for about, I'd say, 20 years at least, perhaps 25 years. Now we have a period when observations and theory are coming together and experimentalists and theorists are talking to each other in meaningful ways, not just where are we going out for dinner. It's truly a very exciting, and I'm learning a lot at this meeting, I must say. I would say that the dark energy is even more of a puzzle than the dark matter, because as Dr. Krauss said, there are some reasonable candidates for what the dark matter should be. There are particles that, in fact, rather too many candidates. There are particles that appear in our theories that could have just, if they existed, have just the right properties to be the dark matter. Whereas the dark energy is utterly mysterious. The mystery is not why there is dark energy, but why there's so little of it. Because, or in other words, it's not why is the universe accelerating, but why is it accelerating so slowly? You would expect, if you just did an order of magnitude, back of the envelope estimate, that the dark energy would be many, many orders of magnitude larger. And the mystery of why it is as small as it is really the bone in the throat of today's fundamental physics. No theory of physics has so far explained this remarkable fact.
Does that mean that you, particle theorists like yourselves, have to go find the missing matter, or come up with an idea for what kind of particles might be out there that answers this question?
Well, the dark energy is not particles. I mean, that's the dark matter. The dark energy is something smooth that particles if they're moving slowly, have no pressure. If they're moving rapidly, they have a pressure which is about a third of their energy density. The dark matter is something with the dark energy is something with negative pressure. And that doesn't come out of any kind of particles. It comes out of the condition of space itself. It's an energy in space itself. We have, as I say, it's not mysterious that it should be there. In fact, any reasonable theory predicts it should be there, but it predicts vastly too much of it.
But only about 5 years ago, we didn't think about dark energy.
That's not true. No, that's not true. We've been thinking about it for a long time. It is true that up until a few years ago, the astronomers kept telling us better and better upper limits on how much there could be. They said it can't be more than so-and-so, and then a few years later they would say it can't be more than so-and-so, which is an even smaller number, and then they found it. The amazing thing is not so much that it was found as why it wasn't there from the beginning, why it isn't in fact so much that the universe would have expanded too rapidly to ever form galaxies.
But to be fair though, Steve, and to Ira, I think that theorists, because there seemed to be so little of it, theorists went into their natural way of trying to solve this. In fact, Steve talked about it earlier. Since there was much less than we expected, we just naturally assumed some miracle must happen and there must be exactly none of it.
Yes,
and that was the assumption until recently.
I think that's fair. If you keep looking for something and it's smaller and smaller than you expect, eventually you say, oh, it's zero for some mysterious reason. But there was a lot of attention for many decades why it's zero. The thing that's changed is now we don't ask why is it zero, we ask why is it so small. But it's been a mystery for decades and decades.
Michael Turner, you want to jump in on it?
Yeah, and I think what's really exciting is that it's a game that we can all play. So the observers now have the ability to probe the acceleration of the universe, and we heard this morning that for the first time we have evidence that this acceleration has only been going on for 5 billion years, that earlier than that, the universe wasn't accelerating. And so the observers are giving us some clues. On the theoretical side, we're very, very excited because this is a big problem. And theorists like big problems. And big problems require new ideas, ideas that at the time may seem crazy. And so both sides, both the astronomers telling us about the acceleration and the theorists making up ideas are having a great time.
I'll bet they are. How do you actually determine what instruments are important in answering these questions, Dr. Turner?
Well, so far it's been the ordinary optical telescope, both ground-based, where the effect was discovered, and space-based. And the property of a big telescope is that it's a time machine. It allows you to look out in the universe, and as you look out, you look back in time. And so you can compare what the expansion rate is today with what it was back then. And what has us excited about the fact that we might answer this question is that some of the other astronomers want to get into this game and play. And some of them will use X-ray telescopes. Some of them will use telescopes in a very intriguing way where they look at how the distribution of matter between us and the distant universe is bent or gravitationally lensed. And some of them are going to use the microwave background to get at this question of acceleration. So I think we're all excited that we're at a point in time where it's worth putting new ideas on the table, and it's worth discussing how to test them, because we're going to have answers in the next 10 years or so.
Dr. Bacall, are all these people getting the same results with all these different instruments?
I think one of the most remarkable things that we hear today, and I've known now for a few months or so, is that all the different observations from different methods, from weighing the universe, to measuring distant supernova, to the microwave background radiation, all of those very different methods yield the same results. They're all consistent results. They all show that we need dark matter in the same amount as we expected some decade or so ago, about a quarter of the total density of the universe. They all are consistent with having some amount of dark energy for the last 3/4 of the total density in the universe. And that's why it is so exciting. I think if you talk to the astronomers, all of us here at the conference, we are just jumping of joy, sitting in our seats and really jump in our seat, because it is a very exciting time to see that the data is all getting together so beautifully. And the main remaining questions are, what does it all mean, as we already heard? Those are the questions for the next decade or so. What is a dark matter? What is a dark energy? What does it all mean for physics?
And are you all agreeing, Dr. Bacall, on what to do next, or are you trying to figure out what to do next?
I think that's part of the discussions that we all are talking about. What are the best ways to go after it? One of the beautiful things in science is that you want to try and get after the answers in different ways. So there are different ways of measuring the high redshift universe, the entire history of the evolution of the structure of the universe, from the bending of light by dark matter, by gravity, from the distribution of the cosmic microwave background radiation and the little fluctuations, the seeds that caused all the structure formation, the evolution of the most massive objects in the universe, clusters of galaxies. All those different methods will continue to be explored. And one of the really exciting things is that there are beautiful data in all these different measurements that are going to come online in the next few years, starting from today up to a decade from now, and we are thinking about what to do even later on.
Let me interrupt, and we'll get back to Cleveland and talk lots more with our scientists about the future of the universe. So stay with us, we'll be right back. You're listening to Talk of the Nation Science Friday. I'm Ira Plato. We're talking this hour about the big questions in cosmology with our guests in Cleveland, all of a very interesting meeting of cosmologists. Lawrence Krauss, chairman of the physics department at Case Western Reserve University. Nobel laureate Dr. Stephen Weinberg, been Neda Bakal, Professor of Astrophysics at Princeton, and Dr. Michael Turner, cosmologist at the University of Chicago. Our number 1-800-989-8255. Stephen Weinberg, you gave a lecture last night. You talked about inflation and the new Big Bang Theory. Can you give us a little thumbnail on what the new Big Bang Theory might be?
Yes, we've heard about the acceleration of the universe that began some number of billions of years ago. Before that, the universe expansion wasn't accelerating, it was slowing down. But it's now believed that there was an earlier period, much earlier, close to what you would normally call the very beginning, when the universe was when the expansion was accelerating, just as it seems to be now. This idea, originally due to Alan Guth and then modified by many other people, seems to solve a lot of the fundamental problems in physics. This early period is called inflation, by the way. But more than that, more than just satisfying theoretical preconceptions, it yields predictions that are being tested, as we've heard at this conference. We're talking about a time, it's hard to talk about how old the universe was or how far back in time it was. I think the best way of saying it is that this is a time going back to when the universe was smaller than it is now, in the sense that particles were closer together. Everything was closer together then than it is now, by a factor of a decimal point and something like 50 zeros and a 1.
Pretty tiny.
Yeah, real small. And this is an incredible reach back. I mean, previously, in our best theories of the universe, we could get experimental information about what happened when the atomic nuclei were first formed, which happened at a time when the universe was, about 10 to the 13 times smaller than it is now. Well, this is 10 to the 50th times smaller than it is now. It's a huge number of zeros following the decimal point that have been added in how far back we can look.
Well, when you arbitrarily say the Big Bang occurred 14 billion years ago, are you talking about that very instant?
I'm talking about something that's such a tiny interval of time that if you said 14 billion years, you would be right, because the amount of time I'm talking about is incredibly tiny compared to 1 year or 1 second. So you could say 14 billion years in the old picture and in the new picture. It doesn't make any difference. This is what happened during that very, very beginning, infinitesimal fraction of a second. And amazingly, our theories tell us that fluctuations due to the quantum mechanics, the same kind of fluctuations that occur inside atoms and keep the electron from falling into the atomic nucleus, these fluctuations at this very early time in the energy of space itself evolved and eventually became what we see in the sky, became a rippling of microwave radiation that comes to us from a much later time, a time when the universe was only about 1,000 times smaller than it is now, and also that we see in the sky in the clusters of galaxies that Professor Bakal studies with her telescopes. We have now observational evidence of this incredibly early time of inflation, and by God, the theories agree with observation. It's amazing how well theory is doing.
It's nice when that happens, isn't it?
Yeah, it's very nice for the theorists. Yeah.
It's not as if there isn't, still a lot of controversy. In fact, I wanted to indicate, the impression one shouldn't get from this meeting is that everyone is in agreement. What's particularly nice is that there used to be no disagreement in cosmology. There was no uncertainty because there was no data. And so what's really nice is to see a data-rich field with lots of different ways of testing the specific details of the theories that Professor Weinberg was was talking about. And so there's so much data that one can just not ask general questions, but one can begin to try and ask the deep questions that we really hid under the rug for a long time.
Yeah. Can you ask us as deep a question as what was there before the Big Bang?
You can ask that, and most of us would say we don't know. But the answer that's probably the least satisfying, but may be true, is that it's quite likely that the concept of time itself began in the Big Bang, and so it may not even be a sensible question. I don't know whether anyone else will have a different answer for that.
Well, that's certainly a possible answer, and one that Stephan Hawking was actively pushing some years ago. Another possible answer associated with the name of Andre Lindy is that our Big Bang is just one episode in a universe that's actually much larger, in which Big Bangs go on all the time, and that in fact, before the Big Bang, there were other Big Bangs, and there will be more Big Bangs in the future, very, very distantly related, very far from anything that we can hope to observe ourselves. Our theories are not yet good enough, and this is really the fault of elementary particle theorists rather than observers, because I can't imagine how observers could settle this kind of question. Our theories aren't good enough to tell us whether time began, as St. Augustine thought, in fact, at the beginning of the universe, or whether time didn't have a beginning, whether this is all going on eternally. We just don't know. But there's no need for us to reach a uniform agreement about this. We're keeping an open mind about this. But I do want to emphasize that it is strange and wonderful that these questions are no longer the province of philosophy, much less theology, but are now part of normal science. That these are questions that are being addressed by mathematical analysis and astronomical observation. And when we find the answer, we'll let you know.
Okay, we'll be waiting.
One thing we would all probably agree on is that there are deep connections between the elementary particles and the universe. And it's reflected in everything we've talked about, and it's reflected in this meeting, and it's reflected in this group here. So we have an elementary particle physicist, we have an astronomer, and we have two half-astrophysicists, Lawrence and myself. And when we look at the solutions to the big questions, they're involving dark matter, a new form of matter that we hope to produce at an accelerator. So it's not just telescopes, it's also accelerators. When we talk about the birth of the universe, or we talk about inflation, we need ideas from the elementary particle physicist, and then we need to turn those ideas around and see how they can be tested with the sky today. So this remarkable idea that Steve talked about, that the largest things that we can imagine, we can't hardly even describe how big a galaxy or a cluster of galaxies is, millions of light years. If this idea of inflation is correct, these things started out as small quantum fluctuations, subatomic size. And even more remarkable than that, we can test it. And the answer seems to be written across the microwave sky, that the biggest things did evolve from the smallest things.
And the universe itself is seen as an experiment. We can do experiments in laboratories, but we can see the universe as one large experiment. The problem for us, and this is something else that's happening at the meeting, is at least in our region of the universe, as far as we can tell, it was only done once. And there are various tantalizing incongruities in the current data that are very interesting to theorists, but the problem is with just one universe to test them in, we may be in a quandary, because in a laboratory you can redo the experiment over and over again. And there are various tantalizing things that I think a lot of people are focusing on. And the interesting question is, will we ever be able to resolve these incongruities being stuck in our own universe?
You've all touched upon the fact, and Dr. Weinberg brought it up first, I think, about the possibility that we're just one of many universes, or there are other universes that have come and gone. One thing that people keep asking me, and is could the dark energy possibly be, we're feeling the presence of another universe next to ours, bumping up against it, and therefore we can't see it, but only the forces get through that little vein there, that little membrane that connects the two of us, but not the light or anything else.
Why not? We are, in terms of
Okay, I like that answer.
in terms of the dark energy, we are looking for crazy ideas. And not all of them are going to be solutions, but we really need, the problem is so hard that it's not just going to be going and looking at Professor Weinberg's calculations and saying, Steve, you know, on page 2, that 2 should have been a 3. And so we need ideas that are very expansive. Most of them will turn out not to be right. Yours too, probably, Ira, I'm sorry to report. But what's exciting is that we can test them. We now have the observations that allow us to get at these ideas, and maybe we'll get the right one, and that will be very exciting.
Yeah, and in fact, the neat thing are the puzzles. So this extra, one of the remarkable things about dark energy is it changes our picture, and we may be in a period of inflation again. And I have to say that my colleague over there, Mike Turner, I know said this before because I've heard him say that periods of inflation are inevitable. But I don't know where he got that from.
Well, it's economic theory.
My comment also on your suggestion, Ira. I don't think it's a real good idea because, as I said, the problem is not why there is dark energy, but why there isn't much more of it. We can calculate that there are lots of things in our little bitty Big Bang that would produce an enormous dark energy. So what you're really suggesting, although you didn't put it this way, is that something from outside is almost completely canceling that. And that is, that's hard to swallow.
There are,
Dr. McCullough, do you want to jump in there? I can't see you, so I don't know if you're getting overrun by the guys there.
Certainly not.
Okay. Let me ask you,
it's very clear that we really don't understand where the dark energy is coming from. So there are many things that we cannot rule out, including your suggestion, although, as was said, it's probably not the most likely suggestion. We discussed today in some informal discussion what is the most likely nature of this dark energy, and it could be just a cosmological constant or vacuum fluctuations, vacuum energy fluctuations. But of course we don't know, and until we have, and the answer will come, first of all, from a better understanding of physics, some theoretical model that will clearly explain many of the other observations and physical phenomenological observations in nature, and from future observations in cosmology, looking at the distant universe, understanding with much higher precision how the universe has evolved over time, and therefore the contribution of this dark energy over time. And the combination of the two will hopefully give us some clues to what the nature of the dark energy is. But the most beautiful thing is, and I like to second what Steve Weinberg said, is that we are now in an era we can measure in detail with reasonable accuracy such mind-boggling things as the existence of dark energy, the existence of dark matter, how much of that, how far does it go, how is it distributed for the dark matter, and so on. Those are things that we could not do 20 years ago when we started. So the questions are now totally different than they were 20 years ago, and the answers are not known to some of them. The answers to previous questions have been answered.
the puzzles become much deeper in a sense.
So, let me just break in and say you're listening to Talk of the Nation Science Friday from NPR News. You see, if anybody's there wants to go to the podium and ask a question, I invite you to go there now. Let me take a call on the phone. Michael in Oxford, Ohio. Hi, Michael.
Hi. I had some questions about parallel universes. The article back in Scientific American back in the spring. I was wondering about the relationship between space and the matter in it, or when we speak of the universe, are we speaking of space, or has space been there before the Big Bang? And as far as level 1 and 2 multiverses,
You've got about 3 questions in there, and let me just focus on the multiverse question that Steve
Explain
touched
to us, people, our ignorant folk like me, what a multiverse is.
One of the ideas that comes from inflation is that this burst of expansion that Steve described earlier was not unique, that there were many beginnings, in fact, an infinite number of beginnings, and that these bubble universes, as we call them, form a multiverse. So essentially, there are many universes. And if you step back and ask what is the most important implication of what we may be doing now, it could be that jump to realize how much larger the universe is than we ever thought. On the other hand, Steve has used the word bone in our throat. It's even worse than that. I think we are completely conflicted about this. The theories say that these different universes and the multiverse idea itself cannot be tested because these different universes are completely separate, that we cannot make observations or detect the presence of these other universes. And so it might well be the most important idea that comes from this time in cosmology, but we just can't test it. And so I think it really has us conflicted.
Well, there may be one way of testing it. In fact, I know Steve has talked about this too, and it's a very insidious way. It has to do with something called the anthropic principle, which a lot of people view as a sort of the enemy of science, and some people have adopted it. And it's the idea that if something is very weird about our universe, maybe it's very weird because if it weren't that way, we wouldn't be here to observe it. And it sounds like it's not science, but the idea, it takes on a potentially real significance if there are many, many different universes and the constants of nature are different in each universe. We might understand why certain things like this dark energy has the weird value it has in our universe only because, if it were much different, there wouldn't be galaxies and there wouldn't be astronomers and there wouldn't be radio hosts to ask the question. And so that may unfortunately be the answer. I think there's a great deal of debate, and we're going to have a very interesting and exciting debate, I hope, tomorrow on that very question. But it may be that if we had a really good theory that explained that the constants of nature were variable and the most likely value was very different than we observed, then it might implicitly suggest that there are many universes and we're in a rare one where life exists.
That's sort of the John Wheeler explanation for why we're here.
Well, Wheeler, I don't think, was thinking of something as concrete as a picture where there actually are where there actually is a multiverse.
We'll come back and talk about it. We have to take a short break, so stay with us. Don't go away. I'm Ira Plato, and this is Talk of the Nation Science Friday from NPR News.
Support for NPR comes from the Noyce Foundation, dedicated to improving math and science instruction from kindergarten to grade 12, and supporting NPR's Science Friday, sciencefriday.com. From the Ford Foundation, a resource for innovative people and institutions on the web at fordfound.com. From the John D. and F. Foundation, now and from improving the understanding of science and technology in our lives. This is NPR, National Public Radio.
What do a neurologist, a poet, and philosopher have to say to each other about consciousness? Join me on the next Science Friday for an interdisciplinary look at the science of consciousness. How do biology, feelings, emotion, and cognition give rise to our sense of self? That's on Talk of the Nation from NPR News. You're listening to Talk of the Nation Science Friday. I'm Ira Flato. Brief program note on Monday's Talk of the Nation. The World Series is 100 years old this month. Look at how it began, how it's changed, and how it shaped baseball. That's on the next Talk of the Nation Monday this hour. We're talking today about cosmology with my guests, Lawrence Krauss, chairman of the Physics Department at Case Western Reserve University, Nobel laureate Stephen Weinberg, University of Texas at Austin, Neda Bakal, professor of astrophysics, Princeton, and Michael Turner, cosmologist, University of Chicago. Our number 1-800-989-8255. Let's go to the audience side. Someone standing at the podium there. Go ahead.
Yes, my name is Vito. I'm a total layperson and work for the post office. My interest in astrophysics and cosmology stems back to the first airing of the Carl Sagan Cosmos series and subsequent PBS specials like The Runaway Universe. I know that Adam Reese was here earlier, was hoping to speak to him. But it also includes Dr. Krauss's books and the first 3 minutes, Dr. Weinberg. My question is, I keep hearing about this cosmological constant that Albert Einstein considered at one point to be his biggest blunder. Now I'm wondering if you all think that his biggest blunder was taking it out.
That's no doubt about it.
Well, I think I would agree with that. Einstein developed a set of very simple equations, and then to try to account for the fact that he thought the universe was not expanding or contracting, but was essentially static, he put in this extra term. And then when he realized that the universe was in fact expanding, he regretted it. But in fact, he was wrong in regretting it in 2 respects. One is he should put in everything that's allowed by the fundamental principles that he was working with, and it is allowed by those principles. So there was never any reason not to put it in. And some purely aesthetic idea of simplicity doesn't really justify not putting in something into the equations which his principles would allow to be there. That's a change in point of view, I think, that's happened in physics. We now take the attitude that T.H. White expressed in The Once and Future King, that everything that is not forbidden is compulsory. But the other reason is a little bit more subtle, and something Einstein should have recognized from the beginning, and that is it didn't work. I mean, when he put in that cosmological constant, it was capable of producing a universe that was not expanding or contracting for an instant, but it was an unstable universe, which would have immediately started expanding or contracting with the slightest perturbation. And Einstein certainly should have known that, and he didn't, he goofed, which is a nice thing to be able to say, because he's the greatest scientist, well, the greatest physicist of the 20th century, one of the greatest of all time. And it's very nice for us now to be able to look back and say, well, he made a mistake there.
And so,
well, that's tough.
1-800-989-8255. Let's go to the phone lines. Let's go to Don in Portland, Oregon. Hi, Don.
Oh, hi, Ira. Thanks for taking my call. I've read recently where some scientists, based on angular measurements of the microwave background radiation, are now saying that the universe is finite and can be shaped like a dodecahedron. I wonder if your guests would like to comment.
Soccer ball. That soccer ball that came out this
There you
week.
go.
That's right. It was just reported this week, and I'm really excited because in exactly 35 minutes, we're going to talk about that at our meeting and rule it out.
We get a preview?
Our meeting's being broadcast live on the web, so you can watch.
I think maybe
There is a recent paper that just came out today that shows from direct investigations from the cosmic microwave background from the WMAP result that rules out this hypothesis. They are not seeing the effect that should have been seen there.
And that's what we'll talk about.
And that's what we'll talk about this afternoon.
But Adam Reese is a pretty heavyweight guy. I mean, could he be making such a mistake?
Well, the bigger they are.
I don't think Adam. It wasn't Adam.
That wasn't Adam Reese.
No,
it was not Adam Reese.
It was someone else. Actually, Adam's made other mistakes.
stir something up, I thought. I actually did. I'm sorry, what were you saying was exciting, man?
Well, what's kind of exciting about the idea is that Einstein's equations don't tell us anything about the topology of the universe, the large-scale shape. It tells us about the curvature, but it doesn't tell us whether the universe is a soccer ball or a donut or something even more bizarre. And so this is an area that we're trying to get at. And I think what's interesting is that we now have the ability to test this idea. And so somebody puts forward this idea, and there are measurements that bear on it, and we're going to hear about them this afternoon. And this doesn't mean that it's not a soccer ball, but apparently it's not a small soccer ball.
Yeah, and exactly. It might have, and as Mike just said, we may argue, prove that it's not a small soccer ball, but in fact, it could be more exotic. There are a lot more exotic possibilities that can't be tested. This is a simple one, and hopefully we can end the debate on it.
Just for the record, this was Jeffrey Weeks who came up with this idea.
The thing is that if the universe has any kind of exotic topologies, then it will look different in different directions. So the more you verify that the universe looks the same in all directions, the more you make it hard for people to imagine some kind of exotic topology.
It shows again the power of the observations in cosmology today to either test and confirm theoretical models or rule them out. And here is a very clear example. There was a specific theoretical suggestion made and immediately ruled out based on the recent CMB observations. There are some theories, following some of the questions we were asked before, multi-universes and so on, that observations cannot test. So there are some things that observations in astronomy cannot test, but more and more so we can test theories, and that's the essence of a good theory, that it's testable. You can either rule it in or you can rule it out.
Kip Thorne told me not too long ago that I told him I thought it was pretty easy to be a cosmologist because no one is wrong. He said no, everybody is wrong. It's trying to prove that you're right is the real problem here. 1-800-989-8255. Let's go to the mic. Who's standing at the mic with a question?
Yes, I have a question with regard to a Scientific American August 2003 article written by Jacob Bekenstein pertaining to the holographic principle and information exchange between physical processes, which he says is a very important development. I haven't heard it mentioned, and perhaps you could elaborate a bit on what the holographic principle is. Is it to be taken literally? And what does he mean by information? And do you need intelligence to interpret information, or can information exist without intelligence?
Who wants to start, Oliver?
Well, I think...
we need a short answer.
To answer the last part, instead of talking about information, you can talk about just the number of possible states, and which is kind of synonym for information, because the information, say, in a memory chip is the information capacity is the number of possible states the memory chip can be in. The holographic principle says that the number of possible states in a volume is not proportional to the volume, it's proportional to the area. And this is something that's true under certain views of quantum gravity. There's still a lot of controversy about it and about its application to cosmology. So far, the applications haven't led to anything that produces a conflict or even any kind of comparison with observation. So it's not playing a big role in this meeting.
But it does. Let me end with something that one of the things. If this dark energy is a cosmological constant, there's probably only a finite amount of information in the universe, and that the implication of that is that life must inevitably end. So I thought that might be a nice way to leave the end.
I'm Ira Plato, and this is Talk of the Nation Science Friday from NPR News. We skirted a little bit. We talked about it before. What role does string theory have? You talked about trying to wrestle around with all these hidden dimensions, I think, 11 dimensions and going up. Can string theory help unite, the two big problems, the problem of gravity and the other forces, and does that help us in understanding the universe? And how? And take any one of those questions.
It might. Has it? In my opinion, no. And the question I want to ask at the meeting is
I think a lot of us, the question that you raised early on, how did the universe really begin? And we need help on that question, and probably from the string theorists, because the standard model that we have, the Big Bang model that goes back to Einstein, begins with what's called a singularity, a creation event. And so we just can't get through that to ask what was before. And I think there is a hope that string theory, which unifies gravity with quantum mechanics, might just be able to help us. And I think the excitement in cosmology over the last decade has really caught the attention of string theorists. And so they are taking their very powerful mathematical techniques and aiming them at that initial singularity and trying to ask the question, what happened before the Big Bang? And I think Lawrence is right that we don't have any big results that we can tout and applaud, but the fact that we have this group of individuals interested in our problems is a very good sign.
You'd all agree?
Yeah, it's a very hopeful, it's a real big hope for string theory to be able to help understand the early universe. And if it's not string theory, we need some other theory. We need something to really go after the very fundamental conditions of the early universe and try to understand.
And it really means that this is the string theorists have gotten interested in this because it's the hottest problem in physics. And I think that's the really exciting aspect, is that this is the big question, and they like to try and answer big questions. And so the fact that it's attracted their attention really means it's really the area to think about.
But you're talking about a theory that has 11 dimensions to it. As experimentalists, and you're experimentalists in the sense of being astronomers, okay, is there any way to prove it by looking out there, finding those 11 dimensions?
No, the theory is a theory that has many phases. There are parameters in the theory that can take a variety of values. And in some region of the space of these parameters, it looks like a flat 11-dimensional theory. But for other values of these parameters, it looks like a 4-dimensional theory. And in fact, space and time don't really appear in the equations underlying the string theory. It's not a theory of things happening in space and time. Space and time arise in the theory as epiphenomena, as something that you use when you want to give an approximate description of nature under certain circumstances. And under certain circumstances, it's 4-dimensional, and under other circumstances, it's 11-dimensional. One of the big questions is, why is it 4-dimensional and not 11-dimensional? But that's not a theory about that's not a question about the underlying theory. That's just a question about what part of the theory are we in? What part of the space of the different parameters are we in?
And it's really early. I mean, it's just really early. That's the problem with too many expectations. It's really early. We don't even really know, I think, what the theory is all about yet, and maybe one day we'll find out.
One shouldn't be impatient. There are good ideas in the past in theoretical physics. There was a theory called the Yang-Mills theory, suggested in 1954. It took a long time to see what it was good for. It was a very beautiful idea, and many theorists were interested in it, but we had no idea what to do with it. And it wasn't for decades before we really understood what use we could make of this theoretical idea. Now it's the basis of our whole standard model of elementary particles.
All right, that's going to be the last word because we've run out of time. I hope it's not another 25 years before we all get together to talk about this. I'd like to thank all my guests. Lawrence Krauss, Professor of Physics and Chairman of the Department of Physics at Case Western. He's also Director of the Center for Education and Research in Cosmology and Astrophysics, and he's also the organizer of this week's conference. Stephen Weinberg, Nobel Laureate in Physics, and Jack S. Josie Welch Foundation Chair in Science at the University of Texas at Austin. Ned McCall, Professor of Astrophysics at Princeton University. Michael Turner, Chairman of the Department of Astronomy and Astrophysics at the University of Chicago. Thank you all for joining us this hour, and good luck to you when you're meeting. We'll listen for the results.
Thank you.
Thank you.
You're welcome. Our program is produced by Annette Heist and senior producer Karen Bergoff. Charles Berquist is our web producer and our director, and our intern is Annalise Strachan. And if you missed any of the references, surf to our website at sciencefriday.com, where you can also
There's something you don't see every day. Jeez, that's a picture and a half right there.
Yeah. A lot of time. We definitely discussed it. Get everybody get their presentation done. Very good with that.
We're not worthy. We're not worthy.
Very much.
People are getting more comfortable with that. The point is not to have the screen. You can't read it. Right. Okay, we got you.
Well, I'm fine, and it's always a pleasure to see you, and I look forward to what you have to say tomorrow about the anthropic principle, and find out what side you're on now.
So you interviewed the man.
It's okay.
Dr. Weinberg, can I shake your hand real quick?
Sure.
Thanks.